So on your intro sheet, Newton's second law is the big one that we spend a lot of time with. Sigma F means sum of all my forces, F net, mass times acceleration. But when we do this, we really break it down into both the x and the y directions separately. And when we go through and we determine what forces are acting on it, we look at only the x's, then we look at only the y's, and then we look overall as a whole. When we sum up the forces in the y direction, I say this a lot, when we sum them all up, it means we add our rights, we subtract our lefts. I'm calling rights and lefts the direction of the forces. So all the forces that are going to the right is your rights, your forces that we're going to add. The forces that are physically, your arrows are physically pointing left, those are the forces we're going to subtract. In the y direction, we add our ups, we subtract our downs. This string of sentence statements is a pretty common thing that we're going to be using, and I'll start using it today already. That when we go through, and if we know one of those statements in that line, every other statement in that line is true. It can't be both this line and this line. It's either this line or this line. But one statement makes everything else in every other statement in that line also true. So, I'm just going to take attendance real quick before I forget. So, if our F net is equal to 0, that means our acceleration is equal to 0, which means my velocity is constant and that my forces in all directions are going to be balanced. However, if my F net is not 0, 1, 18, 57, that's not 0, then my acceleration is not 0. It has some value that's not 0, which means my velocity is going to change and my forces are unbalanced. And that's right what we were working on at the end of class on Wednesday, is we were going through, and on the back side we were looking at summing up some forces in both the x and the y direction. So we looked at situation A, and in situation A, don't mix your x's and your y's, keep your x's and y's separate. But in the x direction, I add my rights. Oh, I'm sorry, let's start with Newton's second law. Sum of all my forces equal to mass times acceleration. I'm asked to find the net force, not the acceleration. So since I don't care about acceleration, I scribble that off, and I can say the sum of all my forces equal to F net. That's what I'm trying to solve for. According to the front side, we add my rights, we subtract my lefts. So for situation A, I added my rights, I added my F applied. I added my applied force, I subtract my lefts, my force of friction, and that's going to give me my F net, which gives me 5 minus 5 for a net force is 0. What does that tell me about my forces in the x direction? My F net is 0, my forces are balanced, my acceleration is 0, and my velocity is constant. In the x direction, only in the x direction is what that tells us. Because we have to repeat this process again in the y direction. Except for in the y direction, now we add our ups, normal, subtract our downs, gravitational force, to give me an F net. So plus 3 minus 3 gives me a net force of 0 in the y direction. So in the y direction, what's true about my velocity? Constant or changing. And in the y direction, my forces are balanced or unbalanced.
Balance.
And in the y direction, acceleration is what? 0. Now if we squash both of those together, as a whole, what's true about my object? In all directions, combine the x's and the y, what's true about my velocity in all directions? Constant or changing? Constant. My acceleration is 0. And my forces in all directions are balanced. But we break apart the x's and y's separately. Okay? I'll do this one more time, kind of the long way, and then we'll kind of expedite this a little bit. So if we look at situation, well here, then overall we can say the F net is equal to 0. Right when we put all that together. So, sum of all my forces in the x direction is equal to F net in the x direction, which is equal to mass times acceleration in the x direction. I don't care about the mass and acceleration. In the x direction, which forces do we add? The ones to the right, left, up, or down? In the x direction, we add our
Left and right.
we add our rights, okay? We subtract our lefts. So we're going to add all of the forces going to the right. There aren't any. So I'm going to put plus 0. It's a placeholder, doesn't really need it, but I'm going to put plus 0. We're going to subtract all the forces going to the left. By name, what's the force going to the left? F of friction, or F of F. I abbreviate a little bit different than they do. Which is equal to F net in the x direction. Plus 0 minus 5 is equal to an F net of negative 5 newtons. What is this negative sign telling me? It's telling me the direction in the x direction, and if it's a negative, that's going to be to the left. So what that means is my left is 5 bigger than my right, which is true. There just aren't any to the right. Now it doesn't tell me and doesn't ask for this, but just for the record, so it's telling me my F net is going to be to the left, right? It also, my acceleration is always in the same direction. So if my F net is to the left, my acceleration is also going to be to the left. They're always pointing the same direction. Now we repeat this in the y direction. F net in the y direction. Oops. The sum of all my forces in the y direction is equal to F net in the y direction, which is equal to mass times acceleration in the y direction. I add my ups or my downs? Ups, which I'm just going to abbreviate F of n, because that's how I do it. Subtract my downs to give me my F net y direction, plus 3 minus 3 is equal to F net y direction of 0 newtons. So what's true about my forces in the y direction? They balanced or unbalanced? They're balanced, which means in the y direction my acceleration is 0 and my velocity is constant. That's the process. And it's really just going through and looking in the x direction and say, are my forces balanced or unbalanced? In the x direction, are they balanced or unbalanced? And if the answer is unbalanced, then it's how much bigger and in which direction are they that much bigger? So if we look at letter C, in the x direction, are my forces balanced or unbalanced? They're balanced. There aren't any, but they're balanced. Okay, they're balanced. What about in the y direction? They're balanced. So if my forces are balanced in both the x and the y, then overall, what is my F net in both directions? It's going to be 0. Which means my acceleration in all directions is going to be 0. And my velocity in all directions is going to be constant. Okay? Does this graph show velocity? Does it show velocity?
No.
Is there anything in here that's actually velocity?
No.
Okay, good. So, bowling ball on the floor. I'm trying. There's a finger roll I'm trying to. There we go. I'm going to lie to you and say, hey, look, this is the free body diagram for that bowling ball sitting on the floor. But if we look at values, I don't know. But if we look at what forces are acting on this bowling ball, this is accurate. It's sitting on a surface, normal force. It's got a gravitational force pulling it down. This is an accurate free body diagram. Whether the numbers are correct, I don't know. But this is an accurate force diagram of what's this bowling ball is acting. So does this bowling ball have an acceleration of 0? Yeah. Does this have a net force of 0 acting on the bowling ball? Yeah. The other thing that could be true, though, let's just pretend that bowling ball is rolling at a constant velocity right now. Okay, if that bowling ball is moving at a constant velocity, what's true about the acceleration? 0. What's true about the forces then? They're balanced. What forces were acting on that bowling ball as it was rolling at a constant velocity across the floor? Was I pushing on it?
Inertia.
There is inertia, but that's not a force that I'm pushing on. It's not an applied force. There was a little bit of friction, yes. But what if we could pretend like that didn't exist, and it was moving at a constant velocity? Then this is the free body diagram for that bowling ball rolling across the floor with a constant velocity. I did push on it, but now I'm not pushing on it. Why is it moving in that direction? There's some inertia that's keeping it moving in that direction. And if we ignore the friction, then this also shows the free body diagram for a bowling ball moving with a constant velocity. The point I'm trying to tell you, this does not tell you whether the object is moving or not. This just tells you whether it's accelerating or not. Okay, keep that in mind. What about this? In D, are my forces balanced or unbalanced? In the x direction.
Balanced.
They're balanced in the x. Good. What about in the y direction?
Unbalanced.
They're unbalanced. Which one's bigger, my ups or my downs? How much bigger are my ups? 15. So what's my net force then? 15 newtons. Which direction? Up. That's supposed to be an arrow. It's a terrible arrow. So my overall net force of this object is 15 newtons up. So I have air resistance up, I have gravity down, I'm accelerating upwards. Oops, didn't draw it. If my F net is up, my acceleration is also going to be up. Now, we don't have enough information at this point in time to determine what is the acceleration, but I can say that it is up. My F net and acceleration are always in the same direction. Okay? So let's kind of go through, this next part is kind of the opposite. So now I give you the F net, now we have to fill in the forces. So if overall my F net is 0, what's true about overall my forces? They're, okay? So in the x direction my forces are balanced, and if I have 50 newtons to the right, then what's A need to equal?
50 newtons.
Has to equal 50. So I add my rights, 50, minus my left, it has to have to add up to 0. In the y direction, are my forces balanced or unbalanced? They're balanced, okay? And if I have 200 down, then I would have to have how many up to make them balanced? I would also have to have 200 newtons upwards to make my forces balanced. Now if my F net is 0, what's true about my acceleration?
0.
It's 0, and my velocity is constant. If my F net is 900 newtons up, 900 newtons up, are my forces balanced or unbalanced? Which direction are they unbalanced? Up. How much bigger are my ups than my downs? 900 bigger up than down, right? So if my down is 200 and my ups are 900 bigger than that, then is what?
1100.
Then it's 1100 newtons up. Which direction is my acceleration going to be?
Upwards.
Up. Yep. What's true about my forces in the x direction?
Balanced.
They're balanced. My velocity's constant, my acceleration is 0. What about this one? 60 newtons bigger to the left. I'm sorry, I gave you too much. My net force is 60 newtons left. My force is balanced or unbalanced?
Unbalanced.
Which direction are they unbalanced?
Left.
And how much bigger are they to the left?
60.
60, right? So if I have 80 newtons to the left, then D has to be,
20.
what's that?
20.
20, yep. So my rights, 20, minus my lefts are going to equal 60 left. Now what this looks like, just for the record, sum of all my forces is going to be F net in the X direction. I'm going to add my, I don't know what to call it, force of D. I'm just going to add D minus the 80, which is going to equal my F net of 60 newtons left. But just so you know, this has to be, would come out to be a 60, right? A negative 60. So when we mathematically do this, this is what would give me the left. Because if I go 1100, oops, that's the wrong one. If I go 20 minus 80, because I'm going to add my 20, that's where that negative 60 is coming in. Just so we're clear on that. If I have an F net to the left, what's true about my ups and my downs? Balanced or unbalanced? So therefore E has to equal 300 newtons down, because up 300 minus my down 300, that's the E to add up to 0. If my F net is 30 newtons to the right, which one's bigger, my rights or my lefts? How much bigger are they? 30. So G is going to be 50 newtons. Add my rights, subtract my lefts, are going to give me 30 to the right. It'd be a positive 30. What about my forces in the y direction? Are they balanced or unbalanced?
Balanced.
They're balanced. So what does F equal?
0,
Could be 0, could be
20.
8,000, it could be 20, it could be any value as long as it's the same as H. So I just said F is equal to H and H is equal to F. But you can make up numbers. You could say 200 and 200, that's fine. But you just got to make sure you keep those forces balanced. I'm going to flip this sheet over and finish the front side. So on Friday, we went through and we filled in everything through Newton's 3 laws of motion. There's a 4th law that Newton came up with. It's not a law of motion, it's called Newton's Universal Law of Gravitation. That is kind of the building blocks of what we are using here. So when we talk about force of gravity, it's a force that we're going to use, and we're going to use this a lot. It's the most common force that we use, because any two objects that have mass have physical attraction, gravitational force towards one another. But the physical attraction between me and that camera is pretty negligible compared to the camera and the Earth, because I'm not very massive compared to the Earth. So the gravitational force that I'm exerting is pretty minimal. In fact, so minimal we don't even talk about it. But it truly does exist. But we use universal law of gravitation as a way to kind of do it. I don't really want to call it a shortcut, but it's more location specific. There we go, formula. So force of gravity up above was one of the forces that had its own separate equation. And its own separate equation is, I often write it like this, and you'll see in a second. It says force of gravity is equal to weight, because that's another term we can use for force of gravity, weight. So if an object weighs 200 newtons, I'm telling you the force of gravity. I'm telling you F of G. I think we're getting close with that focus there. Hopefully. All right, there we go. So my force of gravity is equal to weight. So this is another way we can say that. But in terms of calculating the force of gravity, the way we would calculate the force of gravity is we take m times g. That's the formula. So what does the m and what does the g stand for? The m stands for the mass, so the variable that we use for mass is m. the variable we use for gravitational acceleration is g. So we take m times g. We take the mass of the object times the gravitational acceleration of that location. So when we talk about mass, there's a couple different units we could use. The one that we need to use in our calculations, we have to have mass in kilograms. We need our mass to be measured in kilograms in order for our formulas to come out correctly. Our balances on the table measure in grams. So anytime we do a lab that we physically find the mass of, we put it on our balance. That's going to get in grams. We have to convert it into kilograms. Kilo is a prefix for 1,000. So if you have a kilo of something, like you have a kilo of water, you have 1,000 grams of water. That's what we're measuring, 1,000 grams. About 2.2 pounds, just for the record. 1 kilogram is 2.2 pounds. So we measure mass in kilograms, and what our definition of mass is the amount of matter an object has. Now, the example I'm about to use is not perfect, but I like it from the standpoint of it's a pretty close thing. It's a thought process that hopefully will get you to the right answer. So if I take this eraser, and if I were to go and find the mass, it'd have a certain amount of kilograms, okay, which is fine. But when we talk about what mass is the amount of matter, and when I think of matter, and this is not the perfect definition, but when I think of matter, I think about how many atoms is in this eraser, okay? And if I was going to say, well, what's the amount of matter, I can kind of think of it like, it's not perfect, but I can say, how many atoms is it? And if my number is 10, obviously there's more than 10 atoms in this thing, but let's just make our lives easy. This eraser has 10 atoms in it. There's 10 atoms. I counted every single one. That's the amount of atoms, that's the amount of matter that this thing has. Now, if I take this and I go to the moon, and if I take this eraser and I count the amount of atoms or the amount of matter, how many atoms would I count once I get to the moon? How many atoms are in this eraser when I go to the moon?
10.
10. We did not lose any atoms on the way to the moon, hopefully, because we didn't burn this up as our propulsion, I'm guessing. So we still have 10 atoms when we get to the moon. So did this thing gain mass? Did it lose mass? What can we say is true about the mass based upon its location? Is it independent of location or dependent on location? It's independent. It's independent of the location, which means the location doesn't matter. Okay? It doesn't make a difference whether we're on the moon or whether we are on Mars or whether we are on Earth. The amount of atoms is independent of the location. Now we lie to you a lot in science labs about those aren't scales, those are balances. It's kind of a lie. Actually, it is a lie. We use it to measure mass. Okay, we use it to measure mass. There's a difference between a scale and a balance, though. Okay, you step on a scale to find your weight, right? Oh, look, the scale says how much I weigh. That's a scale. But what's true about your weight? If you go to the moon, is your weight going to be the same or different? Different. It's going to change, right? So a scale is dependent upon location because your weight changes with location. So if I stand on the same scale on the moon, it's going to read something different. So we lie to you and saying, well, that's not a scale, that's a balance. And that balance is going to measure the amount of matter that it has. That type of electronic balance is really a scale because it's calibrated for Earth. And if I were to take this and I were to put it on, if I took that balance, electronic balance, and I took it to the moon and I plugged it in, this is not going to have the same mass, amount of kilograms, because it's going to say it's not the same, because it's not pulling down as hard, right? Now, if we go back historically, what does a balance look like when we talk about like what are we talking about when we talk about a balance? Pirates would measure their gold with a balance, or a thing in front of the Supreme Court. There's a statue where they're holding a balance and it has those pans.
Triple beam balance.
Right? So you use triple beam balances in like middle school, junior high. I don't think we've used them at the high school for a while. But that is a balance, and that would work on the moon. Or if we go with the two pans, actually, like we have one pan and two pans, and we say, oh, we put the eraser in this side, and whoa, we got to put how many bars of gold over here, I don't know, to figure out where it balances. And the idea is if you took that type of balance to the moon, if it took 5 things, pebbles, whatever, to balance it here, it would also take 5 pebbles on the moon. Because balances measure mass. So just for the record, those are technically a scale. We just make it tell us mass instead of weight. So you told me that if you go to the moon, your weight changes. But we said your mass stays the same no matter where you go. So this is dependent upon the location. Your mass is independent of the location. So what must be true about the gravitational acceleration when you go to the moon? Does that change or stay the same based upon location? Is it 9? I've jumped a little ahead. Is this independent or dependent upon the location?
Dependent.
It's dependent, right? So the gravitational acceleration is dependent on the location, and our units that we use to measure gravitational acceleration are meters per second squared. It's gravitational acceleration. Now, we can use Newton's law of gravitation to determine what that gravitational acceleration is at a location. Then once we get there and we know it, then we use G. It's a lot easier than trying to use Newton's universal law of gravitation. Now, G on Earth, before we write this down, let's think back to 1D, 2D motion problems in the y direction. And we made this amazing, like, oh, it's a free fall problem, which means the object moving freely through the air in the absence of air resistance. Because it's a free fall problem, we say that the acceleration in the y direction, and I always wrote it this way very purposely. What is the acceleration in the y direction? What did I always write?
Negative 9.
Before I did that, I always wrote negative g, and then I wrote, which is equal to negative 9.8 meters per second squared. I always wrote negative g, and then I wrote is equal to 9.8 meters per second squared. Now, based on that, what's the value of g? If negative g is equal to negative 9.8, then g equals,
9.
okay, g is a value, a scalar quantity, and g has a value on Earth of 9.8 meters per second squared. G does not have a direction. G is a scalar quantity. When we used g for a motion problem, acceleration does have a direction. And because acceleration does have a direction, we had to tell you the direction, you had to tell me the direction of down at negative 9.8 meters per second. And gravity always pulls towards the center of the Earth. So on Earth, g is constant. Now that's not 100% true. Based upon, g is based upon the mass of the mass of the planet and the distance that you are from the center of the planet, or center of mass to center of mass, technically. So for us, the center of the Earth is the center of mass of the Earth, and right around your belly button is your center of mass. So how far is your belly button from the center of the Earth? That's really what g is dependent upon. Mass of the Earth and how far apart your belly button is from the center of the Earth. Now, if you go up a mountain, you go further from the center of the Earth, right? So, center of the Earth, you're here at Wausau, western Wisconsin, we go up a really high mountain, like, whoa, Rib Mountain, we're way out here. The distance we are from the center of the Earth did change. So technically, g does change. Okay, or we're in western Wisconsin and we go to a really deep mine. Like, whoa, we went closer to the center of the earth. Technically your G changed. It got less. No, it got more. Sorry, it got more. But, like, from the center of the earth to the outer edge of the earth, where we are standing, is really, 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 really big. So the fact that we went up to like Mount Everest was like, oh, we just moved from here to like here. Okay, we barely moved with respect to the distance from the center. So for our purposes, G on Earth is constant no matter where we go. Technically, it does change ever so slightly, but it's so small that it's like indetectable based upon the equipment that you and I would use. Scientists, they could measure it a little differently, but we're not that good at that. Yeah. Did you guys grab a free body diagram sheet on the way in? 2? Free body diagram 2?
Yes.
Okay, if not, I got a couple. You can come and grab. Otherwise, it's lengthy canvas. Okay, anybody else want one? Otherwise, thank you. Anybody else? Okay, they're up here otherwise. Okay, so when we draw free body diagrams, a free body diagram is meant to be nothing more than a quick sketch that talks about the movement, the forces acting on an object. So when we do this, we're looking for keywords, and the things we want to keep in mind is this these string of statements right here, this string of statements right here. These are things I'll be referencing quite a bit. Okay, the idea, oh, the velocity is constant, which means my forces are balanced, my acceleration is 0, my F net is 0. Oh, it's changing, so that must mean acceleration is not 0. So, if we have a book at rest on a tabletop, the fact that they tell me there's a table is significant. And there's my book sitting on a tabletop. Pretty fancy, I know. Here, I'll get nothing but the finest for you guys. Look, the book cover even extends out for all the pages. Wow, that looks just like a book, Mr. Davies. Thank you. Nothing but the best for you. I didn't do that for my last class, just for the record. Only for you guys. Okay, so what forces are acting on this book? Higher gravity. Good. That's always one that you should say, by the way. Gravity, and there's a normal force. Okay? Now, before we start drawing in those things, what kind of information can you tell me about the velocity of this object? It's constant, which means my acceleration is
0,
which means my forces are balanced, and my net force is 0. So my ups, plus add my ups, subtract my downs, it has to give me 0, right? So normal force always goes straight, well, perpendicular to the surface. So there's my normal force. Now our arrows are representative of the magnitude. So the idea is the longer the arrow, the bigger the number. That's all I'm saying. So if we say my book is at rest, which then tells me my velocity is constant, which means my acceleration is 0, my F net is 0, which means my forces are balanced, then what should be true about the length of my arrow going down? Should be pretty darn close to, compared to this, should be the same, right? So I'm not going to measure that with a ruler, but they should be pretty close. If one is bigger, make it obvious that it's bigger. That's all I'm asking for. Okay, my forces are balanced. A girl is suspended motionless from the ceiling by 2 ropes. Diagram the forces acting on the combination of the girl and the ropes. So we have a girl who is suspended by ropes. Ropes. What kind of ropes? What kind of force do we deal with ropes?
Tension.
Tension, right. And how many ropes are there?
2.
2. And which directions are those ropes pulling? one of those two. And the thing with tension that I always think about is, think about if I were to cut the rope or cut the string. If I were to cut it, which direction would the object go? And if the answer is if I cut it and it goes down, then that rope was pulling up. If I cut it and the object goes up, then it was pulling down. Example, girl cut the rope, she would go down. Helium balloon, cut the string, the balloon goes up. Okay, that's the way I think. So because I have two ropes, I'm just going to call FT1, and I have an F. That would have been impressive if I gave me garbage, but I didn't. So my pen died, but we have another force over here that we're going to call FT2. Now normally I don't draw stick figures. I often draw free body diagrams in classes. But I have a force here, and I have a force here. Now my two ropes, I'm just going to pretend, are the same. Their tension is the same. Now, motionless. What does motionless tell us? Tells me the acceleration is 0, which means my F net is 0, which means my forces are balanced. Are there more forces acting on this girl? Right? Because does my picture show balanced forces? No. No. Right now, which way would she be accelerating? Up. She'd be accelerating upwards. So what force is pulling down on her to balance that out? Gravity. Now, quick discussion point. How long should my arrow be compared to this? Bigger, smaller, or the same as this one?
Bigger.
Bigger. What about this one? Bigger. Because what if it was only equal to this? This one. Then it would be this, because this one's pulling up, right? So, assuming that these two are the same length, what should be true about my F of G compared to this one? Should be double, right? It should be double. So, quick approximation, that's about that. Sure, that's, boy, that is spot on double. Okay, so it is bigger, and it's about, this plus this is about the same as this. That's all we're trying to show. All right, one, maybe two more. An egg is free falling from a tree. Neglect the air resistance, right diagram forces. So there's my egg. Free falling. What does that even tell me? Free falling is a...
There's no upward force, just gravity pulling on it.
Yeah, there's only gravity pulling on it. Okay, and it says neglect air resistance, and because of that, my acceleration is going to be negative 9.8 meters per second squared because of this free falling statement, just for the record. But my forces down are bigger than my ups. That's the only force acting on it. However, if we have a flying squirrel, there's my flying squirrel. A flying squirrel, this is the last one we're going to do. A flying squirrel is gliding from a tree to the ground at a constant velocity. Ooh, constant velocity. What does that tell me? Constant velocity tells me that my acceleration is, which means my F net is 0, which means my forces are balanced. Okay, so what forces are acting on my flying squirrel?
Gravity.
We have force of gravity, which is about that big according to my arrow. And we have wind resistance, or what do we call it? Air resistance, yeah. So now we have an upward force, and what should be true about with this arrow compared to this arrow?
Same.
They should be the same. Again, I'm not getting a ruler out on these, but if one was bigger, like oh, then we should make that force bigger if it is bigger. Okay, we'll pick this up tomorrow. This worksheet is going to be a homework sheet. It's not something you need to work on tonight. I'll give you a little bit of time. We'll do like one more problem probably, and then we'll move on. So let me know these. This is the building blocks. I said this is probably one of the hardest chapters, and it starts with free body diagrams. That's why we're starting there before we put any numbers in. Have a good day, everyone.